So we've already looked at diffraction through a slit, but what is a little different but usually more useful to us is if we look at diffraction through a circular hole. When light goes through a small opening, it spreads out in all directions. Whatever direction you tried to confine it, it spreads out most that way. If diffraction didn't exist, or if we have extremely large openings, the light will give us a perfectly sharp shadow. So, for example, if we use height to try and represent intensity, and we have uh, this gray card here with a hole cut in it and the light shining through the hole, the light would be uniformly intense all the way across the face and perfectly sharp edges. Right? We'd have down here we'd have a perfectly bright circle and then perfectly dark right beside it. Uh, the real result, if the holes are not huge compared to the wavelength of light, actually kind of looks like this. Remember, height is intensity, so very bright at the center and then trailing off as you move away. But actually, some places where it gets dark and then gets bright again and then gets dark again. There's actually an ad of a drop of milk falling into a bowl of milk in super slow mo, and it looks a lot like that. This ripple in a pond kind of thing. The cross section of it, if we just took a slice of it, it would look like this. So that would tell us intensity is very high here, but it drops off, and then we get dark spot, bright, dark, bright. And since we're rotating it around, we get this thing. So it's going to look like a bullseye, a set of light and dark rings. And the reason this is important is we want to know a lot of times, are we looking at one source of light or two of them that are really close together? One of the things that this affects is how well can a spy satellite see what it's looking at? How well can a mapping satellite tell you what the ground looks like? Uh, on the science end, it's a lot more common to use this to figure out, is this telescope looking at one star or more than one star? And the reason is, while human twins are fairly rare, when you look up in the sky and see a bright spot, somewhere between a third and a half of the time, when you do that, you're really looking at a double star system. Uh, the only way we can figure out a planet's mass or a star's mass or an asteroid's mass or whatever, we can't put it on a giant scale anywhere. We have to use Kepler's third law, which Newton modified back in 1111, and figure out the period and the orbital radius of one of the satellites. Now, planets are usually too far away and too dim for us to use them to try and figure out the mass of the star they orbit, although the James Webb Space Telescope may change that a little bit. So these double star systems are perfect for that. You can see both stars and you can follow them. If you ever take usually a second semester astronomy course, intro course, where you look at stellar astronomy, galactic stuff like that, what you'll see is just about everything we know about stars and galaxies can be traced back to finding the masses of stars through this method. So what we care about right now is, how do we know whether we're looking at two stars or one? And this depends on how well the telescope can resolve them. We don't want some subjective thing like one astronomer says, I think I see two, and another astronomer says, I think I see one star there. So we need something objective. And the criteria that just about everybody agrees is if the peak of this weird shape overlaps the first minimum, the first valley of the one next to it, then we say they're too close together and it's just one star. If they're more separated than that, we say, okay, that's pretty clearly two stars. Different way we could look at it here are our weird hat-like shapes again. When the peak, if it overlaps the valley, they're too close. They got to be more spread out than that when we look at them. Now, when we were looking at diffraction through a slit, we just needed to find out where sine theta equals m lambda over d, and that would locate the first minimum for us. This happens whenever theta is pi or 2 pi or 3 pi, any integer multiple. This weird shape that we've drawn is actually called a Bessel function, and finding the places where it's zero, that's not as easy as it is with sine. You don't have to worry about that. All it means to you is the formula changes by a little bit. our first minimum, instead of being sine theta is just 1 times lambda over d, is 1.22 times lambda over d. So that's the only change. This is from that Bessel function, this extra factor. So theta is always going to be a small angle, or we wouldn't be trying to decide if we can see these things, if they wouldn't be so close together if it was not a small angle. So we use the small angle approximation that says theta and sine theta are about the same thing when you're in radians. And we can say, all right, the angular separation here, the resolving power, is 1.22 lambda over d. In some books, they use a capital R for this. Here, what you actually want, the better telescope has a smaller value of R, because what it's telling you is things can be closer together, and this better telescope can still see 2 of them instead of 1. Notice that this only depends on the size of the opening, the big lens in the telescope or your pupil or whatever, and the wavelength of light. So we could use this formula to get a good idea what the resolving power of your eye is. How good do we expect a person can actually see 2 dots as 2 dots? So for our lambda, what we would pick is the middle of the visible region, since that's where our vision is best. That puts us at about 550 nanometers, which is green. D is the diameter of your pupil at night. Remember, this is just the black spot in the center of your eye, not the colored part of your eye. We say this is about 7 millimeters. So this would give us a resolving power, if we plug in 1.22 lambda over d, of 0.0000959 radians. One thing to notice, by the way, you notice here we're in meters, right? 550 times 10 to the negative 9 meters. D has to be in meters also. If I put the top in nanometers and the bottom in millimeters, I'm just going to get garbage. The units have to cancel out, the lengths, the distance units have to cancel out, so that all that's left over is an angle. What is this in degrees? Well, we could multiply by 180 divided by pi. That would tell us it's 0.0055 degrees. That's still really small, so can we use something smaller than degrees? We can use arc minutes, and we say that 1 degree can be broken into 60 arc minutes. We use a little apostrophe as the symbol for that. So that means if we then multiply this by 60, we would say about 0.33 arc minutes is your eye's resolving power. We can also use arc seconds. There are 60 of those in an arc minute. So your eye's resolving power, we could say, is about 20 arc seconds. Now, you're not actually ever going to get to this level. Your eyes are not going to be this good unless you get out into space, because the air will screw things up, and it affects the resolving power of everything, your eye, big telescope, whatever. So it's limited by the atmosphere rather than by diffraction. This is a reason why putting telescopes in space is such a big deal. If the Hubble was on the Earth, it wouldn't be in the list of the top 40 largest telescopes. The reason it's, even 100 years ago, it wouldn't have been the largest telescope. The reason it's so important is that it's in space. So it can get to its theoretical resolving limit. So we use the same wavelength of light, and its main mirror is 2.4 meters. So we put in the numbers here, and we get 0.06 arc seconds. This is, of course, ridiculously better than your eye. This is better than we'd get even at high altitude observatories in Hawaii. Now, interesting side note, the best spy satellites the United States has are probably basically Hubbles that are pointing at the ground. They're the same diameter, but they're just pointed at the ground. If they're 400 kilometers away and they have a similar resolving power here, what can they see? Well, we go back to radians to make our life easier. We get this for the resolving power in radians, about 3 times 10 to the negative 7. Now, if 2 points are 400 kilometers away, and this angle between them, as far as the observer is concerned, we want to find out what x is. So we know d, and we know alpha here, and we want to know x. Remember, alpha is our resolving power. D is our 400 kilometers from the satellite to the ground. Ordinarily, we'd have to use trig to do this. We'd need the tangent function. we'd go through all this, but remember that in this case, d is enormous compared to x. So we can do the small angle approximation again. Sine theta and tangent of theta are all about the same. So what we get is our angle is just x divided by d. So when we plug in our resolving power for our theta, what that tells us is if things are 11 centimeters apart from 400 kilometers up, these spy satellites can detect them. Whether this could pick out a particular face, I don't know, but it's not very far from it. It could certainly see there is a face there. We would get better results if we had shorter wavelengths, and we get poorer results if we have long wavelengths. That's not necessarily a choice we get to make unless we're just making up physics problems, though, because everything you look at has a wavelength where it is brightest, and it may not emit anything at the shorter wavelengths that you might prefer to use. So radio telescopes, for example, have horrible resolving power. The biggest one in the world is in China, and it's 500 meters across, so that's coming close to 6 football fields. The shortest wavelength it can see is about 10 centimeters, so that gives us a resolving power of about 1 arc minute. So 1.22 lambda divided by d, we convert it to degrees, convert it to arc minutes, about 1 arc minute, and your eye is better than that. Of course, your eye can't see radio waves. The images from small radio telescopes look a lot like what weather forecast images look like, the blobs of high pressure and low pressure. They're not completely, they're not complete blobs. There is some shape to them, but they're not far from it. However, modern telescopes can now do something. They can use interferometry, which we talked about in the last chapter. And what that does is we combine multiple telescopes, their data streams, and we can put them together as an interferometer that gives telescopes the resolving power that would be like a telescope with a diameter equal to the baseline, the separation between the telescopes. So in other words, we could never build a radio telescope the size of Earth, but if we put 2 of them on opposite sides of the Earth, we'll get the resolving power equivalent to that. So if we did that, we've got our 1.22 over lambda. 2 times the Earth's radius is the distance between them. We multiply by, turn it into degrees, arc minutes, arc seconds. Here we've got 0.002 arc seconds. This is better than the Hubble. And again, of course, it's a different frequency range, but this is not actually as good as having a single radio telescope the size of the Earth because it would gather a lot more energy than the little ones, but we also can't expect to build one that big. For resolving purposes, it's just as good. If you were going to have this on a test, you might have a question like, you've got an infrared telescope with a 40 centimeter aperture or mirror, and you're looking at light of wavelength 1.75 micrometers. You've got 2 sources, 0.05 meters from each other and 10 kilometers from you. Do you see them as 2, or do you just see a single blob? The first step is to find the resolving power of the telescope. It's 1.22 lambda over d. Notice these are all things that you could basically calculate this once for a telescope and engrave it on the side. It's not going to change no matter what you look at. It's a fundamental property of the telescope, just like your eye's resolving power is a fundamental property of your eye. So here we get 5.3 times 10 to the negative 6 radians. What's the angular separation of the 2 sources? That's their distance from each other divided by their distance to us. That's 5 times 10 to the negative 6 radians. If you look at this one's really close, but the fact that this is smaller than the resolving power means those sources are a little bit too close together for us to pick them out as 2 different sources. If we had a little bit bigger telescope, if they were a little bit further apart, 6 centimeters instead of 5, if we got a little closer, 9 kilometers instead of 10, we'd be able to see 2 blobs. But as it is, we would just see 1.